All right, so this is the second video of the unit, um, and it's on what's called electric current and resistance and resistivity. So the objectives for this, looking at basic ideas of current and calculating math with current with potential difference, looking at what's called an ohmic and non-ohmic material, and then looking at the difference between resistance and resistivity. All right, so current is really just how fast electric charges pass by a given area. So like water flow looks at how much water passes a given point. Electric current looks at how much charge passes a given point. And its charges and current is in coulombs per second. The current is in amps. Now you might have heard about that before. Amps is the measure of current, how fast the charge goes. Okay, so you have electric potential, which is in voltage, and you have current, which is how fast the charges pass by a given point. So the higher the current, the more charge passes by in a given amount of time. Okay, so we're going to watch a little video clip here.
Electric current is the net flow of electric charge carriers from one point to another. The charge carriers can be negative, positive, or a combination of the two. Which is the case is not a concern for most applications. For this reason, scientists have chosen to treat most electric currents as if they were entirely due to the movement of positive charges. This equivalent current is referred to as conventional current. For many applications, it is not important whether the negative charge carriers are moving in one direction or the positive charge carriers are moving in the opposite direction. In these cases, scientists treat electric current as if it were entirely due to the movement of positive charges. The conventional current is a current that has the same net movement of positive charge as the actual current. In the case of a current within a metal, the actual current is due entirely to the movement of negatively charged electrons. If the electrons, which are negatively charged, move from right to left, the conventional current is an equal amount of positive charge moving from left to right. In particle accelerators, currents can consist entirely of moving protons. In this case, the conventional current is the same as the actual current. In some gases and dissolved salts, current can be due to positive charges moving to the right and negative charges moving in the opposite direction. In this case, the conventional current would consist of positive charges of an amount equal to the total movement of charge, but all moving to the right.
So you don't have to necessarily worry about all of that. Just understand it's the rate that charge moves. So again, current is how fast the charges move. It's measured in amps. And now we're going to look at what's called resistance. Okay, basically the opposition presented to electric current. When something doesn't allow the current to travel through, that's called resistance. Okay, and when the resistance happens, that energy, the electric energy in there, is converted to some other form, typically heat or light. It's actually what causes the light bulbs to light up. You have that resistance that takes energy out. It doesn't allow it to flow through, and it gets converted to something else. The SI unit for resistance is ohms, and it's 1 volt per amp. 1 volt of potential difference divided by amp or per amp of current. And the equation is this. So resistance is potential difference divided by current. Okay, so you can also look at this as potential difference is resistance times current. Okay, so there's an idea, because resistance is measured in ohms, there's this idea called an ohmic material. Now this Ohm's law is this mathematical formula. Resistance is voltage over current. That's Ohm's law. So anything that follows Ohm's law is said to be an ohmic material. The resistance is constant over potential differences. It's ohmic. Okay, other things that aren't are called non-ohmic materials. And the resistance of a material depends on multiple things. Depends on how long the object is. Depends on how wide it is, the cross-section area, how hot it is, and really actually the overall composition of the material. Okay, we're going to watch another quick little video clip here.
The resistance of a length of wire depends on several factors: its length, its cross-sectional area, the material it is made of, and the temperature of the wire. Long wires have more resistance than short wires. This is because the current must force its way through a longer path. Similarly, a wire will have more resistance if it is very narrow. The current must all push through a tight space in order to flow. Copper is among the very best conductors of electricity. Metals such as iron or aluminum are more difficult for current to flow in. Higher temperatures also cause high resistance. This is because the random vibrations of the metal atoms can disrupt the flow of current. Consequently, the very best wires to use for low resistance would be short, thick wires made of copper and kept at a low temperature.
Okay, so just to review, the longer the wire, the greater the resistance. The skinnier the wire, the greater the resistance. If it's not copper, typically has a greater resistance, and the hotter the temperature, the greater the resistance. Okay, so ideally you want a short, wide, copper, really cold material, because that has the lowest resistance. And the colder the resistance, the more basically just means the more freely electric charge can move through it. The hotter the current, the hotter the wire, the more resistance there is, because the current doesn't want to flow in one straight path. Okay, so now there's this other property called resistivity, and we're just going to do a little bit of difference here. So resistance, really, it's opposing the flow of electrons. And again, its units are in ohms. It depends on the length, the area, and the temperature. Then you have this thing called the resistivity of it, which is really the resistance of a material with specific dimensions. Okay, so resistivity kind of depends on the resistance. The unit is ohm meters. Okay, and what I want to do is I'm going to show you a little bit of an example here to get the formula for resistivity. Okay, so again, the resistance is proportional to the length. So the longer the wire, the more resistance there is. And the resistance is inversely proportional to the area. So the bigger the area, the smaller the wire. And you end up with this formula. Resistance is P is resistivity times the length divided by the cross-sectional area. Okay, because the bigger the cross-sectional area, the lower the resistance. Okay, so the resistivity is dependent upon different materials at certain points. And you will be asked to rearrange this resistivity equation and look at what things cause changes in resistivity. Okay, now we've talked about resistance, which is not allowing charge to flow, resistivity, which is really just a property of resistance, current, which is how fast charge flows through. Now let's look at the two main types of electric circuits that charges can flow through. So they are series and parallel. A series circuit, a circuit is something that just electric charge can move through. A series circuit, the electric charges can only flow through one path. Parallel circuit, there's multiple paths for these things to go through. Okay, so here's a basic diagram with 3 light bulbs. The series circuit, the parallel light bulb, or in the series circuit, the battery just makes one loop with light bulbs. The parallel, if you look at it, makes different loops to each light bulb. Now I want to show you a little simulation that kind of demonstrates what's going on here. Okay, so this one is a series circuit. I've got a battery, wires, I've got these 2 light bulbs, and we're going to make a complete loop. Okay, so if you notice, it shows the electrons moving in a circle. Now, if I break apart one of these wires right here, just cut it, neither wire or neither battery light bulb can light up because there's not a complete charge that moves across it. Because if you notice with this, the current just makes a circle. Okay, the current just flows in a circle. And all I'm doing, if I break a spot for this, I'm not allowing the current to go in a circle anymore. Okay, so that's a series circuit. They're in one big loop with whatever the power source is. This is like the old school holiday lights where if one goes out, they all go out. Okay, so that's a series circuit. So now we have a parallel circuit. And if we look at this one, so we've got multiple loops for current to travel through. So I'm going to connect all the wires. And if you notice, the electrons, once they leave here, they can split right here. They can go one of two ways. They can either go to that light bulb or they can go to this light bulb. So what I'm going to do is I'm going to turn off essentially this light bulb. I'm going to detach it. And if you notice, this light bulb still lights because there's multiple paths for the electrons to move through. So I'm going to reconnect these, disconnect the top one, and this light bulb still lights up. So multiple paths for current to travel through. Okay, most of your light bulbs are wired in parallel, where if one goes out, you know it, and you can figure out what's causing it. You can just look at changing that one light bulb. Okay, so current is how fast charges move through a given area. Resistance is how much charge is essentially taken out of these. So these light bulbs have resistance. Resistivity is like a property of resistance. And you have these electric circuits. This should be enough for you to finish the Google form. And please ask questions in class about the electric current. Have a good day.